Welcome to this LeetCode video solution to problem 21, merge two sorted lists. The problem gives us two linked lists, which are sorted in increasing order. We are to merge the two lists into one large sorted list, and this is to be done by splicing the nodes of the two lists together instead of copying the values into a new list. Our constraints are that the total number of nodes in each list is between 0 and 50 inclusive. The value held in each node is between -100 and 100 inclusive, and both lists are stored in increasing order. Let's look at how to approach this problem. Let's start with a linked list. A linked list is a data structure consisting of nodes where a node contains a value and a reference to another node. By making these nodes point to each other, or linking them together, one can create a linked list to contain a series of values. By passing around the reference to the first node of the list, also known as the head of the list, one can manipulate the entire list. Unlike an array, a linked list does not have a constant access time for each value at an index. This is because in order to access a value at an index, we must traverse from the head of the list each time, as all we have is the reference to the head. However, one can add more elements onto a linked list by keeping track of the tail and making it point to a new node. In contrast, adding a new element to an array in Java requires creating a new array that's greater in size by 1 and copying all the values from the old array into the new one. The question asks us to return a sorted list that consists of the nodes of our two provided lists. That means we can't copy the values from the given lists into new list nodes to make our result list. We have to somehow take the nodes from our provided lists and rearrange them such that they point to each other and are in sorted order. The easiest way to do this is to look at the start of each list and take the node with the smallest value. We can compare the next two nodes at the start of each list and take that smallest node, adding it onto the list we're building. Because the nodes in the remaining two lists are equal to or greater than the smallest node we've found, and they are in sorted order, the next smallest node taken from these two lists is guaranteed to have a value that is greater or equal to the previous smallest node we have found, and is also the smallest value in the two lists. Once we get to the end of one list, we can just add on the rest of the other list because we know the remaining nodes will all be greater than or equal to the end of the list we will return. To do this, we just need to return the head of the other list and have the tail of our result list point to it. We can do this because the head of the list still has a reference to its next node. We don't need to iterate over the rest of the list and keep adding its nodes, as they are all still connected through their references with each other. As you can see, all we've done is rearrange the nodes in the provided lists to point to each other in one new list, while keeping them in ascending order. One way to implement this solution is to do it recursively. Recursion means that our problem can be broken down into sub-problems, or smaller versions of the same problem. For example, our problem is our function that, given two lists, will return them as one merged sorted list. So, in the process of merging two sorted lists, is there a subproblem within that process where we can use the sorted list we get from merging two sorted lists? Can we break the problem down into similar subproblems, where we can use the functionality of the very function we're writing? Let's go through the algorithm step by step and try to find a place where we need to merge two lists. Firstly, we are given the head of two lists. We compare the values of these nodes and take the smaller of the two, to which we can add on the next smallest node. We are left with two lists. Now, instead of just getting the next smallest node, wouldn't it be nice if we could just have these two lists be one giant sorted list already, that we can add onto the smallest node we have just found? Because the remaining nodes in the two sorted lists are greater or equal to our smallest node, we know the head of the returned list will be the next smallest value, thus preserving our ordering. Some of you may have noticed that this is our recursive case. We're applying our function to a smaller case within itself, and within the recursive call, the same thing is happening again. It finds the smallest node and calls itself to get the sorted list to add onto it, and so on. At this point, all we need to do is add the sorted list to our smallest node, and then we can return the result. However, what will the function do when it reaches the end of a list? A null pointer exception would happen, as we're trying to access the value of a null. we need a base case to stop the recursive call from happening. Our base case is when either list is null. If one list is null, we can return the head of the other list. The time complexity for the recursive approach is big O of m plus n, where m is the number of nodes in our first list and n is the number of nodes in the second. This is because, in our worst case, we have to iterate over every node in both lists and add them to the new list to return. The space complexity is also big O of m plus n. This is because every recursive function call takes up space on the call stack, and we have at most m plus n calls, because for each call we are comparing the next node of one list to a node from the other list. Let's see how we can translate our algorithm into code. Firstly, we have to compare the heads of L1 and L2, the first nodes of our two given lists. What we're looking for is which one is smaller. Then, when we know which of the two nodes is smaller, we can assign that to be the head of our returned list. So we need, firstly, the node to return. Then, we can compare L1 and L2. And we'll see if L1 is less than L2. We know that we can assign head to be L1, the first node in L1. Then we've got to move L1 to the next node along. Likewise, if L2 is smaller or equal, it doesn't matter which one it is because they're the same value, then head equals the first node of L2. And we make L2 equal to L2.next. So now that we have our smallest node saved in head, we can merge the remaining two lists together and add that on to head. So head.next is equal to merge two lists of L1 and L2. This is going to return us the two remaining lists merged together in ascending order of size. After that, we can just return head. However, we must also consider our base case, otherwise this could continue to go on forever. Or we hit a null pointer exception. In this case, when we reach the end of one list node, what we want to do is return the other list, in case it might still have nodes in it. So, in this case, if L1 is null, then we can return L2. Likewise, if L2 is null, then we can return L1. So when we reach the end of one list, we can return the end of the other list. And if L2 happens to be empty, that's also fine, because that just signals the end of the two combined lists. So the time complexity is big O of m plus n, where m is the number of nodes in the first list and n is the number of nodes in the second list. This is because we have to go over every single node in both lists using merge two lists, taking one off and then recalling this entire method on the two remaining lists. Likewise, the space complexity is also big O of m plus n, for the same reason. We are calling this m plus n times for every single node in the list, and that is proportional to the number of stack frames being used. There is an alternative solution to this problem, which has an improved space complexity. The recursive solution takes up space on the stack frame with each recursive call, with a space complexity of big O of n. An iterative solution would not need this allocation of memory, and therefore should have a constant space complexity. In fact, a common follow-up question asked in interviews for recursive solutions is, could you solve this iteratively? This is because an iterative solution is usually more optimal as it has a smaller space complexity. The iterative method is as follows. We iterate over the two lists and take the smallest node of the two, creating a new list we can return. The only difficulty with this approach is that we must keep track of a number of pointers. Let us think about what pointers we need. Firstly, we need to keep track of the heads of the two lists. Whenever we take the smallest node off of a list, the next node in the list becomes the head, and thus the node we will compare. We can use the existing L1 and L2 variables for this. Secondly, we need to keep track of the tail of the new list we are making. This is because when we take the smallest node off of a list, we need to put it at the end of the new list, so we can use a reference called tail to access the node at the end of the list, so we may add new smallest nodes. Part of our problem, our head and tail aren't pointing to anything. This causes a subtle difference. The first time we have a smallest node, we must make tail and head point to it. But every time after that, to add to the list, we must make tail.next point to the smallest node. We can solve this by creating an empty list node and having head and tail point to it, so all we need to do is make tail.next point to the smallest node every time. Now we have all of our pointers, we can go through our algorithm. We compare the nodes at the head of our two lists and have tail.next point to it. Then, we must move the head of the list we have taken a node from to the next node, representing the start of the remaining list and the next node to compare. At the same time, we must move to tail.next, so it's at the tail of the new list. We repeat until we reach the end of one list. At that point, all we have to do is add the remaining nodes from the other list to tail.next. We can then return head.next because head currently points to the empty node before the head of the list. The time complexity is big O of n plus n, as we are performing the same comparison operation on every node from each list. The space complexity is constant, because all we are doing is manipulating the pointers that already exist with the nodes in the lists provided. At most, we use memory for our pointers head and tail, but the space used by them does not grow in proportion to the number of nodes in the lists. Let's look at how to translate our algorithm into code. First, we need to keep track of a number of pointers, beginning with the head that we're going to return and the tail where we're going to add nodes onto. So, we're going to initialize our head to a new empty list node. And then we're going to initialize our tail to point to head, so they're pointing at the same place. So now we have our initial pointer set up pointing to an empty node. We can iterate until we reach the end of one list. So that is, whilst L1 is not null, and L2 is also not null. This is because, eventually, we'll update that head to point to the null pointer that the last node in that list is pointing to. We can now compare the heads of the two lists. So if the head of L1 is less than the head of L2, we can add on that node to tail.next, adding it on to the list we're going to return. And then we can move L1 to the next node in that list. Likewise with L2, we can do the same thing, if L2 is smaller or equal to L1. We can then move tail along to tail.next, where tail.next is the node we have just added on. This makes sure that tail is kept up to date with the end of the list, so we can keep adding on nodes to the correct location. Once we've completed iterating over the two lists, what we're left with is one empty list, either L1 or L2, and potentially the other list containing nodes still. If the other list contains nodes, what we can do is we can set tail.next to point to those remaining nodes. We can do this by asking the question, is L1 null? We can use a ternary operator for this. If L1 is null, then we can return L2, which should be pointing to the remaining nodes in L2. Otherwise, we can use L1. And then we can just return head.next, as head is pointing to the empty list node. So the first node of our list is actually the node right after the empty head node. The time complexity is big O of n plus n. This is because we have to iterate over every node in both lists in our worst case. The space complexity is constant, because all we have to keep track of for any size m or n of either list is the head pointer and the tail pointer. This has been the video tutorial for Merge Two Sorted Lists. Thank you for watching.